Welcome back to the deep dive. If you're building anything serious in the cloud, you are dealing with data. And if you're dealing with data, you are absolutely dealing with storage.
That's for sure.
Today, we are opening up the hood on one of the most fundamental architectural pillars in AWS storage services. And, this is absolutely vital knowledge for anyone tackling the Solutions Architect Associate exam.
That's right. We're getting into Domain 3, designing high-performing architectures. And the core lesson here, really, isn't just knowing the acronyms S3, EBS, EFS.
Right.
Our mission is to equip you with the fundamental choice. How do you decide between object, block, or file storage? You have to select the right tool based entirely on the access pattern and the performance your application actually needs.
Because if you're coming from an on-prem world or you're just starting out, you might think, well, storage is storage. You put a file on a disk, you read it from the disk. But AWS fundamentally separates these three, and if you mix them up, your performance will just collapse or, your costs will skyrocket. We need to synthesize the difference.
Okay, let's unpack this. I think using some strong, memorable analogies is the way to go here. We have three completely distinct ways to organize and access data.
Let's start with the one that gives us that raw, uncompromising speed we often need, block storage.
Block storage, which in AWS is the Elastic Block Store, or EBS, is the most, let's say, traditional model. Think of it as a raw, dedicated hard drive that's, attached to a single server.
Okay, a dedicated hard drive.
Exactly. Data is chopped up into these fixed-size chunks, or blocks. What makes this so fast is the lack of management overhead. The server knows exactly where block 1, block 2, block 3 are.
So it's very low latency.
Ultra-low latency.
Yeah.
And because it's so fast and granular, it is the dedicated choice for things like high-performance relational databases.
So it's one-to-one, incredibly precise, and it has to be fast because a database just cannot wait.
Precisely. When we talk about database speed, we talk about IOPS input-output operations per second.
Right, the number of reads and writes.
Yeah, how many specific reads or writes can happen in 1 second? Block storage delivers the highest IOPS because of that low overhead.
Perfect. So if block is the dedicated high-speed drive, what happens when we need to share that data? That seems to lead us right to file storage.
It does. File storage, or EFS in AWS, is your classic corporate shared folder system.
Ah.
So instead of blocks, it uses a hierarchy we all recognize. Files nested within folders within directories. And crucially, EFS uses standard sharing protocols like NFS, the Network File System.
And that protocol is the key.
That's what allows multiple servers, a whole fleet of EC2 instances, to mount, read, and write to that exact same storage volume at the same time.
So the architectural distinction is already clear. Block is singular, dedicated speed. File is all about shared accessibility.
That's the core difference. And then you have the third major paradigm, which is object storage. This one is, well, it's the big one. Think of object storage, Amazon S3, like a massive infinite warehouse.
I like that, a warehouse analogy. So how is the data structured differently in this warehouse?
Every piece of data, a photo, a log file, a video, is treated as a single complete object. It doesn't live in a file system hierarchy. It just lives in a flat global bucket.
No folders.
No folders. Instead, it has metadata, a detailed digital packing slip or barcode attached to it that describes the object, its size, creation date, and so on.
What's the architectural consequence of structuring it like that?
The consequence is that you retrieve the whole object. If you need to change, say, a single line of code in a 5 GB file.
You can't just edit that one line.
No, you have to download the entire 5 GB, modify it on your machine, and then upload a brand new version to S3. This gives you scale that is basically infinite, but you sacrifice that ability to do really granular, low-latency edits.
Okay, that makes perfect sense. So object for scale, file for sharing, block for that surgical single-instance speed.
You've got it.
So let's spend a moment on S3 then, the king of scale. If I'm a huge company archiving petabytes of data or, hosting every single photo from millions of users, S3 is really the only choice.
It is the only choice for unstructured data at that kind of scale. And architecturally, you have to remember two specific things about S3. First is the scale. It is virtually unlimited.
Right.
Second is the durability. S3 offers 11 nines of durability.
That number 11 nines, it always sounds like a bit of a marketing term. Can you translate that into what it actually means for us?
It's astonishing, but it's critical.
Well,
11 nines, so 99.9999% durability, means that if you store, say, 10 million objects, you can statistically expect to lose one of them every 10,000 years.
wow.
It's an insane guarantee that your data just won't be corrupted or lost.
Okay, that puts the safety factor into perspective. But S3 isn't a silver bullet, right? You mentioned it has a trade-off with consistency.
It does, and this is a critical detail. S3 is eventually consistent for certain operations, particularly overwrites. Because it's distributed globally, when you update a file, it might take a moment, usually milliseconds, sometimes longer, for that new version to propagate everywhere.
Wait, so if I'm rapidly overwriting a critical config file, some of my servers might see the old file while others see the new one. That sounds like it could cause chaos.
It could, and that's why it's an acceptable trade-off for the right workload. You gain that unlimited capacity and durability for static data. You accept that tiny risk of inconsistency because S3 is best for data that's written once and read many, many times.
Like images, videos, logs.
Exactly. If you need immediate confirmed global consistency for every single write, you shouldn't be using S3 for that function. You should be using a database.
That solidifies it. So if you see unstructured data, static website hosting, or archive petabytes, you're thinking S3.
Spot on.
Okay, let's pivot to the other extreme. Pure performance. The storage equivalent of a race car engine. We're talking Amazon EBS.
Yes, block storage. If you're running a massive SQL database and need storage to feel like it's physically hardwired to your EC2 instance, you need EBS.
It's that devoted, high-performance personal hard drive for that one instance.
It is. Its primary job is to deliver high IOPS and ultra-low latency. Because if a database transaction lags even a little, the whole application feels it.
And like we said, that devotion comes with a major constraint. An EBS volume can typically only attach to one single EC2 instance at a time. It's an exclusive relationship.
Exactly. And the real architectural challenge here is selecting the right type of EBS volume because they vary wildly in cost and speed.
I found the distinction between GP3 and IO2 to be the key hurdle when I was looking at this.
It is the defining choice.
Okay.
So you have two main flavors to understand. First is GP3, the general purpose volume. This is your balanced choice, good for most things, like standard web servers or medium-sized databases.
Okay.
The key detail with GP3 is you can scale the IOPS, that transaction speed, and the throughput independently of the storage size. You don't have to buy a huge terabyte disk just to get good performance anymore.
That's huge for cost control. So GP3 is the flexible, budget-conscious choice.
Precisely. Then you have IO2, or provisioned IOPS. This is the premium option. If your requirements include words like mission critical, massive transactional databases, or requires a guaranteed performance baseline,
Then you're paying for IO2.
then you're provisioning an IO2 volume. The distinction isn't just IO2 is faster. It's that IO2 guarantees that minimum performance level, which is critical for meeting strict service level agreements or SLAs.
I see. So the choice pivots on whether your performance is negotiable or if it's actually mandated.
That's the architectural insight. If an SLA says you must process X transactions per second, you can't rely on burstable performance. You need the guaranteed, consistently high IOPS that IO2 provides, even if it costs more.
Okay, that makes the trade-off really clear. Let's move to our team player scenario. Imagine I've got a massive WordPress site running across dozens of EC2 instances. They all need to access the same theme files, same config, same user uploads all at once. S3 is too slow for that file system feel, and EBS is exclusive to one machine.
And that's where we bring in Amazon Elastic File System, EFS. It solves that multi-server access problem perfectly. It's a fully managed NFS, or network file system.
So it speaks the language the operating systems already expect.
Exactly, allowing all those EC2 instances to share the storage transparently.
And the major feature, the thing that makes EFS so popular, is its scalability model, right?
Absolutely, the killer feature. Unlike EBS, where you have to provision the size beforehand, EFS is elastic. You just create it, and it automatically grows as you add files. You pay for what you use, and you never have to worry about running out of space.
That must be perfect for variable workloads.
It is, and I can imagine it's ideal for big data processing, too. If you have a cluster of instances that all need to analyze the same raw data, EFS gives them that unified shared workspace.
For sure. Any scenario where you need parallel access to a single file system, content management, shared code repositories, EFS seems like the go-to.
It's the ideal persistent storage solution for that pattern.
Okay, so we've established the three fundamental cloud storage types, but when we talk to businesses, we know most of them aren't 100% in the cloud. They have on-prem data centers, and they need to bridge that data into the cloud for, say, durability and backup. How do we do that?
For that, we rely on the AWS Storage Gateway. This is literally the bridge. It allows on-prem applications to leverage cloud storage as if it were local. The key here is providing cloud-backed but local speed access.
What does that actually mean, local speed? How does it do that if the data is going to the cloud?
It all comes down to caching. The gateway sits locally in your data center, and it acts as an intermediary cache. It holds the most recently accessed data right there.
Oh, okay.
The rest of it, the vast majority you rarely need, is safely backed up to S3 or EBS in AWS. So your local users get fast access to current files, but you gain the cloud's extreme durability for your long-term storage.
That's smart. And the gateway comes in a couple of different modes, right? Depending on if the data is files or blocks.
It does. The most common one is the file gateway. This presents itself to your on-prem servers as a standard network share, using protocols like SMB or NFS. The applications think they're writing to a local server, but secretly, the gateway is sending all that data to an S3 bucket.
So it's basically transparent durability.
Precisely. And then you have the volume gateway. This is for when your on-prem apps rely on block storage, like for traditional database backups and disaster recovery. It provides block-level access and manages snapshots that get stored in AWS.
Okay, that gives us the full picture. Let's pull this all together. Let's run through the decision matrix one last time for our listener.
Sounds good. The summary is pretty clean. If your key requirement is sheer scale for unstructured data access via an API, you use S3.
Object storage.
Yep. If you need raw database speed and low latency for a single instance, you use EBS.
Block. And remember to match the volume type GP3 for flexible, IO2 for mandated SLAs.
Exactly. And if you need to share files across many machines with an auto-scaling file system, you use EFS.
Which is file storage. And if the problem involves bridging an on-prem location,
Then you implement the storage gateway.
that's a clear breakdown. But if we connect this all back to the bigger picture of successful cloud design, what is the ultimate criterion? What dictates whether you choose right or wrong?
It always comes back to analyzing the access pattern. That is the ultimate criterion. You have to ask, is the access pattern one instance or many? Is the application using a web API, which suits S3, or does it expect a full file system hierarchy, which points to EFS?
If you identify the access pattern first, the choice of service becomes obvious.
It really does.
That raises a really important question and something for you to mull over. We spent time defining the ultimate speed, like IO2 provisioned IOPS. But when you're building a genuinely hyperscale, low-latency application like a high-frequency trading platform, what if the requirement is so high that even IO2 is barely adequate? Does the architectural decision pivot from just choosing the right storage to designing the entire application to bypass storage limitations altogether?
That is precisely the next level of architectural thinking. It shifts the discussion from how do I make the storage device faster to how do I use the storage device less often, right? The real performance gains in those extreme cases often come from intelligent use of in-memory caching or changing how you manage state. You're pushing the limits of compute rather than just waiting for a faster disk.
Absolutely. Think about that idea. The fastest storage is the storage you never have to hit. Thanks for diving deep into the foundations of cloud storage with me.
Always a pleasure.